Alright, let me start talking to you the way I'd actually start thinking about this if you and I were sitting in the same room, maybe with a cup of coffee, maybe with a blackboard nearby that I promise not to use too much. You've been told your whole life that gravity is a force. Something pulls on you. The earth grabs you. Apples fall because the earth tugs on them the way a magnet tugs on a nail. That sounds perfectly reasonable. In fact, it sounds so reasonable that nobody ever asks the obvious question. How does the earth reach out and grab you? I don't mean poetically, I mean literally. You're standing there minding your own business, and this enormous rock called Earth is somehow influencing you across empty space. No strings, no rods, no hands, just pull. That's already strange, but we get used to it. Human beings are very good at getting used to strange things if they work often enough. Now let me give you a little uncomfortable thought. Suppose you're in an elevator, the cables snap, and suddenly the whole thing is falling. The floor, the walls, everything drops together. Inside you feel weightless, you float, your coffee floats. Your stomach does that funny flip, and here's the disturbing part. As far as you can tell, gravity has vanished. Completely. Gone. But wait a minute. The Earth didn't disappear. The mass of the planet is still there. According to the usual story, gravity should still be pulling on you just as hard as ever. So why don't you feel it? That's the crack in the story. Tiny crack, but once you see it, you can't unsee it. If gravity were a force like other forces, you should feel it no matter what you're doing. If an electric field pulls on a charged particle, it doesn't politely stop pulling just because the particle is falling. If a magnet attracts iron, the attraction doesn't vanish when the iron starts moving. Forces don't care about your emotional state or whether you're falling or standing still. They just act. And yet gravity behaves like a shy creature. When you stand on the ground, you feel heavy. When you fall, gravity somehow disappears from your experience. That's already very suspicious. Here's another one that bothered me when I first really thought about it. Imagine you're deep in space, far away from stars and planets. No gravity anywhere. You're floating peacefully. Now someone turns on a rocket attached to your spaceship and it accelerates upward. Suddenly, you're pressed into the floor. Your feet feel heavy. You could drop an apple and watch it fall to the floor exactly the way it falls on Earth. Now tell me honestly, without cheating, how do you know whether you're on Earth or just accelerating in empty space? You don't. There's no experiment you can do inside that sealed box to tell the difference. Every little test you invent, dropping objects, watching how things move, feeling your own weight, gives the same result. That's not a cute coincidence. That's a deep problem. Because if gravity were a normal force, it would be a completely different physical situation from acceleration. A force is something that acts on you. Acceleration is something you do. These are supposed to be different ideas. And yet nature is telling us very stubbornly that they are indistinguishable. That's like discovering that heat and motion are secretly the same thing, which, by the way, also turned out to be true. Nature enjoys playing this kind of trick on us. Now let me make it even worse. If you jump off a cliff, please don't, but imagine it, you are in free fall. In that state, you feel no gravity. Your body follows the most natural, effortless motion it can. No strain, no stress, just motion. So when do you actually feel gravity? Only when something stops you from moving the way you want to move. When the ground pushes up on your feet. When a chair pushes on your back. When a rope pulls on your hands. That sensation you call weight is not the earth pulling you down. It's the ground refusing to let you fall. That's upside down from the way we're taught to think. We say, gravity pulls me down and the ground holds me up. But your body's own experience is exactly the opposite. Falling feels natural. Being held up feels forced. So now you have to ask a dangerous question, the kind that gets physicists into trouble. Maybe gravity isn't really a force at all. Maybe it's something else entirely. Let's try a little thought experiment, because thinking is cheaper than building large machines. Imagine you're an astronaut drifting past the Earth, not falling straight down, just gliding sideways. You don't feel anything special, no tug, no pull, you're just moving. But your path slowly curves around the planet. From far away, someone watching you might say, ah yes, gravity is pulling him in. But from your point of view, nothing is pulling. You're just moving forward, minding your business, following the smoothest path available to you. Smoothest path through what? That's the real question. We're used to thinking of space as an empty stage where things happen. Objects move through space, forces act in space. Space itself just sits there like a grid on graph paper. But suppose space isn't just sitting there. Suppose space itself has structure, shape, geometry. Suppose moving straight near a massive object isn't the same as moving straight far away. In the same way that walking straight on the surface of the Earth eventually brings you back to where you started. No force pulls you toward the North Pole when you walk around the globe. You're just following the geometry of the surface. Straight lines on a sphere look curved when you draw them on a flat map. Now your instincts should be screaming, wait a minute.
Space isn't a surface! I can go up and down!
True, but instincts are trained on everyday experiences, not on the universe's private bookkeeping system. What if gravity is what happens when space and time themselves are curved, and objects are simply following the straightest possible paths inside that curved geometry? Then falling isn't being pulled. Falling is doing nothing at all, and standing still on the ground is actually the unnatural thing. The ground is constantly forcing you off your natural path through space and time. That idea feels wrong at first because it insults common sense. But common sense is just a collection of prejudices acquired by age 18, as someone once said, and I happen to agree with him. The more you poke at gravity, the more it refuses to behave like a proper force. It doesn't have a direction you can shield against. You can't block it. You can't turn it off. It affects all objects the same way, regardless of their mass or composition. A feather and a hammer fall together if you remove the air, which is already a hint that gravity doesn't care about the things forces usually care about. Forces normally depend on charge or mass or some property of the object. Gravity seems oddly democratic. Everything participates whether it likes it or not. And then there's time. Time always sneaks into the room when gravity is around, even when nobody invited it. Clocks tick differently near massive objects. Time slows down near the Earth compared to far away in space. That has nothing to do with pulling or pushing. That's geometry again, that's structure. So now we're in an uncomfortable position. We have a phenomenon we call gravity that looks like a force if you squint, but behaves like geometry if you pay attention. It disappears when you fall. It reappears when you're prevented from falling. It can be mimicked perfectly by acceleration. It treats all objects equally, and it messes with time. At this point, you should feel uneasy. That's good. Uneasiness is the first sign that you're learning something real. Because once you seriously entertain the idea that gravity is not a force, you're forced to rethink what motion even means, what space really is, and whether falling is the right word at all. And if you're wondering how far this rabbit hole goes, and what kind of universe you end up with when you stop thinking of gravity as a pull and start thinking of it as a shape, then go ahead and tell me to keep going. Good, because once you've swallowed that first uncomfortable idea, your mind starts doing what minds do best. It starts poking at it from all sides like a child with a loose tooth. So let's play with it a little more, but gently, because this idea breaks if you handle it the wrong way. Think about something you already understand without realizing you understand it. Take a map of the Earth, a flat map. On that map, the shortest path between two cities looks like a curve. Airlines draw these funny arcs that seem to bend toward the poles. People look at them and say, that can't be right, that's longer. But then the airplane flies it anyway, and it turns out to be the shortest route. What went wrong? Nothing. The mistake was assuming the flat map tells the truth about straight lines. On the surface of a sphere, the straightest possible path looks curved when you force it onto flat paper. Now imagine you're an ant living on that surface. You don't know about spheres. All you know is forward. You walk straight ahead, never turning, and somehow mysteriously, you end up circling the globe. You could invent all sorts of explanations. Maybe there's a force pulling you sideways. Maybe the ground has opinions about where you're allowed to go. But none of that is necessary. The geometry already did the job. Now here's the trick that makes gravity weird. We don't live on a curved surface of space. We live inside space. And time is mixed up in it too, like an ingredient nobody labeled. So let's simplify. Forget planets for a moment. Forget stars. Imagine a universe with nothing in it at all. No matter. No energy, just space and time. In that universe, if you throw a ball, it moves in a straight line at constant speed forever. That's not because nothing is pulling on it. That's because that's what straight means there. Now you add a little mass, just a bit. You don't add a pulling force. You just add mass. And suddenly the meaning of straight changes near it. That's the leap that hurts the brain, because we're trained to think that objects move first and forces act later. But here, the stage itself changes. Space and time rearrange their rules, and objects, obedient little things that they are, simply follow the new rules. Let me give you something you can almost feel in your bones. Imagine you're rolling a marble on a rubber sheet stretched tight. The sheet is flat, and the marble rolls straight. Now put a heavy bowling ball in the middle. The sheet dips. Roll the marble again. It curves inward. People love this analogy, and they also love to misunderstand it. They say, the marble rolls down the slope. But that explanation sneaks gravity back in through the back door. The rubber sheet works because Earth's gravity pulls the marble downward. So don't take it literally. Take it emotionally. The point is not that things roll downhill. The point is that what used to be straight isn't straight anymore once the geometry changes. In the real universe, mass changes the geometry of space and time, not just space. Time too. And that's crucial because everything moves through time whether it wants to or not. You're moving through time right now at a steady pace, 1 second per second, no exceptions. Even if you sit perfectly still in space, you're racing through time. That motion is unavoidable. Now here's the sneaky part. In a curved spacetime, moving straight through time doesn't look like staying put in space. It looks like falling. So when you're standing on the Earth, you're actually being forced off your natural path. Your natural path is free fall. The ground interrupts it. The ground says, no, you're not allowed to follow spacetime straight lines. You must stay here. And your body feels that protest. That protest is weight. That's why you don't feel gravity in free fall. You're finally allowed to move the way spacetime wants you to move. Now let's do another experiment, one you can try at home without breaking anything. Take a bathroom scale. Stand on it. It reads your weight. Now jump. For a brief moment, the scale reads 0. Did gravity turn off? Of course not. What turned off was the resistance. The scale only measures how hard it has to push on you to stop you from falling. When it doesn't have to push, it has nothing to report. So already, even before fancy mathematics, your bathroom scale is whispering the secret gravity isn't what you think it is. Now suppose you're inside that falling elevator again. You float. You can juggle objects. You can pour water and watch it form perfect spheres. Every experiment you do screams the same message. This is an inertial frame. This is the most boring state of motion possible. Boring is good in physics. Boring means simple. Boring means no forces, so free fall is the boring case. Standing on the Earth is the complicated one. That should flip your intuition completely upside down. And if it doesn't yet, let's keep pushing. Imagine two people falling toward the Earth from slightly different positions. They start out parallel. As they fall, they slowly drift closer together. Not because they're attracted to each other, but because they're both following space-time straight lines, and those straight lines converge. From far away, it looks like a force pulling them inward. From up close, it's geometry playing its quiet game. This also explains something else that used to bother me. If gravity is a force, where is its energy stored? For electric and magnetic fields, we can point to the field itself. For gravity, things get slippery. The energy bookkeeping becomes strange, non-local, almost embarrassed. That's because we were asking the wrong question. We were trying to assign force, like properties, to something that isn't a force. Once you see gravity as geometry, some mysteries dissolve instead of being solved. And here's another delightful insult to intuition: light bends in a gravitational field. Light has no mass, so if gravity were just a force that pulls on mass, light shouldn't care, but it does. Why? Because light follows straight paths too, and when space-time is curved, straight paths curve. The light isn't being pulled, it's just being honest. Now, you might be thinking, all right, fine, maybe gravity isn't a force in this grand cosmic sense, but down here on Earth it sure feels like one. Yes. And so does centrifugal force when you take a sharp turn in a car. That doesn't make it a fundamental force either. It's a convenient way to describe what happens when you insist on using a non-natural frame of reference. Calling gravity a force works extremely well for everyday life. Just like saying the sun rises works extremely well if you're not launching satellites. Physics doesn't throw away useful ideas. It just quietly replaces them with deeper ones when they stop making sense. And the deeper idea here is that motion, when you strip it to its bones, is about geometry, about path, about what straight really means. Once you accept that, gravity stops being this invisible hand reaching across space. It becomes something subtler and in some ways more beautiful. The universe isn't tugging on you, it's guiding you along its shape, and the really unsettling part is that this shape isn't just out there. It includes time. It includes the ticking of clocks, the aging of bodies, the sequence of cause and effect itself. So when you fall, you're not being dragged downward. You're drifting along the contours of reality. And that raises a dangerous question, one that starts to pull us away from analogies and into the raw machinery underneath. If gravity is geometry, then what exactly is being curved? How is it curved? And how does that curvature decide where things go? That's where the story stops being friendly and starts being astonishing. All right. Now we're far enough in that we can't pretend anymore. Up to now, we've been flirting with the idea, circling it, poking it with analogies and intuition. But at some point, if you're honest, you want to know what's really going on under the hood. Not equations on a chalkboard for their own sake, but the logic of the thing. The internal reason gravity behaves the way it does. So let's talk about what's actually being curved. It isn't just space, and it isn't just time, it's space-time, a single object. You don't get to pull them apart once gravity enters the room. That already sounds abstract. So let me anchor it to something physical. Think about how you locate an event. Not a thing, but an event. I drank coffee. That happened somewhere in some time. You can't describe it with space alone, and you can't describe it with time alone. You need both, coordinates and space-time. Now here's the crucial idea. Motion is not about where you are in space. Motion is about how you move through space-time. In a gravity-free universe, space-time is flat. Not flat like a table, but flat in the geometric sense. Straight paths stay straight. Two objects released side by side stay side by side forever. Introduce mass and energy and space-time curves. And once space-time curves, straight paths do strange things. The technical word for a straight path in space-time is a geodesic. Don't worry about the word. Think of it as the path of least effort. The path that requires no pushing, no pulling, no resisting. The lazy path. Nature loves lazy paths. A planet orbiting a star is not being yanked around by a force in this picture. It is moving lazily along a geodesic in curved space-time. From far away, it looks like a curve. Locally, right where the planet is, everything feels straight. That's why astronauts orbiting Earth feel weightless. They are not half pulled or balanced. They are falling freely, following space-time's geometry perfectly. Now here's where time sneaks back in and makes everything stranger. Mass doesn't just curve space. It curves time more strongly than it curves space. That's not a poetic statement. That's a measurable fact. Clocks closer to the Earth tick more slowly than clocks farther away. We have to correct for this in GPS satellites, or your phone would think you're standing in the wrong city. So when you're standing on Earth, your feet are aging more slowly than your head. The difference is tiny, but it's real. Your body is stretched across slightly different rates of time. Now imagine what straight through time means in that situation. If time flows more slowly near the Earth, then moving straight through time naturally pulls you toward regions where time flows more slowly. That motion through time shows up as motion through space. This is the part that people don't usually hear, and once you hear it, gravity never looks the same again. Objects fall because they are trying to take the straightest possible path through time. They are not being pulled downward. They are sliding into regions where time runs slower. From the outside, it looks like acceleration. From the inside, it feels effortless. This explains why gravity treats all objects the same. The path through space-time doesn't care about mass or composition. It cares about geometry. A bowling ball and a feather differ in air resistance, not in how space-time tells them to move. And it explains why light bends. Light always takes the straightest possible path through space-time. When space-time curves, light curves, no force required, no mass required. Now let me address something that tends to bother people at this point. They say, fine, but you still haven't told me why mass curves space-time. That's a fair complaint. And the honest answer is, that's where we hit bedrock. We have an equation that tells us how mass and energy relate to curvature. On one side is the geometry of space-time. On the other side is the distribution of mass and energy. The equation balances perfectly. Change one, the other responds. But why does nature choose that equation? That's like asking why energy is conserved or why the speed of light is the same for everyone. At some point, physics stops explaining and starts describing. A good description that never fails is the next best thing to an explanation. And this description works frighteningly well. It predicts black holes. Not just vaguely, but precisely. Objects so dense that space-time curves inward so steeply that no path leads back out, not even for light. The idea of force completely collapses there. Nothing is being pulled. There simply is no outward direction left in space-time. It predicts gravitational waves, ripples in space-time itself. Not waves in space, but of space and time. We've now detected them. We've listened to space-time ring like a bell after two black holes collide, and here's a subtle point that always makes me smile. In this picture, gravity is not something that propagates through space-time the way light or sound does. Changes in gravity are changes in space-time. You're not sending a signal across the stage. You're reshaping the stage. That's why gravity is so weak compared to other forces. It's not competing on the same playing field. Now let me bring it back to something human, because physics without humanity is just bookkeeping. Every day you are prevented from following your natural space-time path by floors, chairs, shoes, and bones. You spend your life being pushed around by normal forces so that you don't do the one thing the universe is gently encouraging you to do fall. When you lie in bed at night, the mattress pushes you upward so that you don't follow space-time's curve into the earth. That push is what you feel. That push is what aches. That push is what we mislabel as gravity. Gravity itself is the quiet part, the background instruction manual of reality. Once you see that, the idea of a gravitational force starts to feel like a shadow of a deeper truth. Useful, yes. Fundamental, no. And now we've arrived at a point where the physics starts bleeding into philosophy, whether we like it or not. Because if gravity is geometry, and geometry shapes motion, and motion includes time itself, then gravity is not just about falling apples and orbiting planets. It's about how the universe allows events to happen at all, which raises the final, unavoidable question: what does this say about reality, about time, and about our place inside a universe where falling is the most natural thing you can do? That's where this stops being just physics and starts feeling a little unsettling. All right, let's finish the thought, but not by tying it up neatly. Nature rarely does that. It prefers to leave you a little uneasy, because uneasiness means you're still thinking. Up to now, gravity has slowly stopped being a thing and started being a relationship. Not a pull, not a push, a structure, a rule book written into space and time themselves. And once you really accept that, something strange happens to the idea of down. Down is not a direction in space. There is no universal arrow pointing downward in the cosmos. Down is a direction in space-time. It's the direction your straightest possible path happens to point when you're near a massive object. That means when you fall, you're not being dragged toward the earth like a helpless object. You're doing the most honest thing you can possibly do in this universe. You're following reality's contours. Standing still on the ground, on the other hand, is an act of rebellion. Think about that for a moment. All your life, you've been told that rest is natural and falling is something that happens when things go wrong. But the universe tells a different story. Free fall is the natural state. Standing still requires constant resistance, constant force, constant interference. Your bones, muscles, floors, chairs, buildings all work nonstop to keep you from doing what space-time quietly prefers, and that flips something deep inside your intuition. It suggests that the universe is not a place where objects are pushed around by invisible hands. It's a place where motion emerges from structure, where the rules come first and the behavior follows. Now let's zoom out, because gravity really only makes full sense when you stop thinking locally. From far away, stars move, galaxies spin, clusters dance. It all looks dynamic, energetic, almost violent. But underneath, there is a calm geometry guiding everything. Planets are not struggling to escape their stars. Stars are not wrestling with their galaxies. They are all gliding along paths laid out by space-time's shape, like leaves carried by a river whose flow they don't feel. And time is part of that river. This is the part that quietly messes with your sense of self. You are not just located somewhere. You are located somewhere. Your life is a path through space-time, a curve, a world line if you like names. Gravity doesn't just influence where you go. It influences how fast your time flows along that path. That means gravity shapes aging. It shapes memory. It shapes causality. It decides which events can influence which other events. In a strong gravitational field, the future and the past are squeezed closer together. Near a black hole, the idea of later becomes fuzzy. Inside one, the concept of elsewhere may disappear entirely. At that point, words like force and motion become almost childish. The universe is no longer throwing things around. It is arranging possibilities. And here's the thing that always gets me. This enormous, abstract, mind-bending structure is not something you only encounter in equations or observatories. You encounter it every time you stand up. Every time you feel your weight, you are feeling the refusal of ordinary matter to let you follow space-time's natural curve. Your sensation of heaviness is a signal that geometry is being interrupted. Gravity itself is silent. This also changes how you think about freedom. In a strange way, free fall is the freest motion there is. No forces, no constraints, just geometry doing what geometry does. That's why astronauts talk about orbit as peaceful. That's why falling dreams feel so vivid. Something deep inside you recognizes that motion as familiar, even though you're taught to fear it. Now, I don't want to oversell this. Calling gravity not a force doesn't mean the old picture was wrong. It was incomplete. Newton's gravity is a brilliant approximation. It works because space-time around Earth is only gently curved. For everyday purposes, the universe is polite enough to let us pretend, but when you push beyond that politeness, when you ask deeper questions, the universe answers with geometry, and that answer has a quiet philosophical sting. It means the universe doesn't need intentions. It doesn't need pulls or pushes or desires. It only needs structure. Once the structure is there, everything else follows. Mass tells space-time how to curve. Space-time tells matter how to move. That's not a story about control. It's a story about consistency. and you are part of that consistency, not separate from it, not watching it from the outside. Your heartbeat, your aging, your thoughts unfolding one moment after another, all trace a path through this curved space-time. You are not in the universe. You are a process happening inside its geometry. So when you ask, why does gravity exist? You're almost asking the wrong question. Gravity isn't something added on top of reality. It's part of the grammar reality uses to make sense of itself. And maybe the most unsettling realization of all is this: if gravity is not a force, then falling is not failure. Falling is obedience. Obedience to the deepest rule the universe has ever revealed to us, that the shape of reality decides the motion of everything within it, including you, including now, including the very next second you are about to experience. And the strange, beautiful, humbling part is that whether you understand it or not, you are already following that path perfectly.